let's start. Okay, so hi everyone. So we are going to start chapter 3, which is about vector valued functions. So this is chapter 3, and it's about vector valued functions. So there are several things we want to study in this chapter. One of them is, first of all, what is a vector valued function? I mean, this concept is important. And related to this concept that I will define right now is the idea of continuity. And even before continuity, we should also discuss limits, before that. So I better write it in the right order then. So it's limit and continuity. There is also the idea of derivative for such functions. Then we will look at the idea of tangent line. So then we look at curves in space. Tangent line. Then we look at unit tangent vectors. And so I should say tangent vectors and tangent line, maybe that's better. Tangent vectors, tangent line, and unit tangent vector. Then we discuss a very important idea, which is the idea of arc length. For a curve in space, we're going to tell you how to measure the length, basically. So that's arc length. And kind of the overall, the ultimate goal, everything we do in this section, is leading towards this concept of curvature of space curves, basically. So, curvature of space curves. So that's really a cool topic because you may have seen in one variable calculus curvature of curves in plane. But here, we are talking about curvature of curves that are in space. And this is a bit more complicated and certainly more interesting. It's related to that idea of curvature that you already know, but it's a bit more involved. So that's kind of the overall kind of the highest point of this, I should say, of this chapter is to get this curvature of space curves kind of properly defined, and then the rules to calculate such things. So that's the overall goal of this chapter. So these topics we will discuss in this chapter. Okay, so let's start with this first part, which is vector valued functions. What are they, and how we can formulate and kind of what's a good notation for them. So maybe right here. So vector valued functions. So this is basically any function f that goes from some interval AB on the real line to R3. I mean, the interval doesn't have to be a closed interval. It could be the whole line, for example, also. That's possible. It could be half closed, half open. All kinds of things is possible. So, or something like this, for example, is also okay. Basically, what this does, it takes this one-dimensional line and puts it somehow in three-dimensional space, in any which way you can imagine. It maps the line into this three-dimensional space. So the geometric picture of this, so this is a concept, but the geometry of this is like this. You can have this in mind. Here is, okay. So for example, so we have this interval AB. This is on the line, right? And then we have this function f that takes you from here into the three-dimensional space, right? One-dimensional space to three-dimensional space. So this point, for example, is the initial point, is f of a. And this point is the final point, f of b. And anywhere in between, if this is t, for example, this is f of t. So as you move from A to B, this curve, we say curve, moves from f of A in space to f of B, right? So this is, so geometrically, we can say that such a thing is really just a curve in space, right? It's just a curve in space. So a curve in space. Okay, so this concept is important. We have the notion of curve in space, which is geometrically this, but in terms of notation, is this one. Yeah. Not yet, but I will tell you how to define continuity and then. But for us, abstractly, it's just any map right now. Yeah, we are not assuming right now, but very soon we will, indeed. Very soon we will assume. Okay, good. Any other questions or comments? Okay, so good. So that's it. So what is the notation for such a curve? The notation is something like this. I mean, yeah, it's a vector notation. So we just say f of t equal to f1 of t, f2 of t, f3 of t. Right. So we just say t is between b and a. Of course, you can also write it as f1 of t I using those three coordinate vectors, f1 of ti plus f2 of t j plus f3 of t k. So f is given completely by these three functions, f1, f2, and f3. Sometimes there is another notation is used instead of f. It's also common to use r for radius or for radial vector or something like that. So also r of t equal to x of t, y of t, z of t, etc. is used. So we can have many different notations, but they all refer to the same thing. It's just a notation for a curve in a space. You can also imagine a particle moving in space in some way. Maybe there's a satellite or there's some rocket or something moving in space. It's following these paths. And we want to have a relation formula that describes the position of this particle at time t. That's the position of the particle at time t. That's what. So we have that. Okay, very good. Now, your question, which was about continuity and limit and this sort of stuff. So everything that you learn in calculus, one variable calculus, we're going to shift it to this functions from R to R3 now. So for example, we can talk about limit of function. So limit, so let me give an example before that. So here is something like this, R of t equal to sine t, imagine, cosine of t, and t. And I tell you the domain of this function to be less than infinity, bigger than minus infinity. So the domain is everything. In other words, I haven't specified a finite part. I just say the domain is everything. So the question is, what kind of curve this equation specifies? What curve is this? Right. So that's the question. By asking what curve, I don't mean you tell me exactly what shape the curve is. Just give me kind of profile of this curve. That would be enough. Yes?
Is it like a helix, like spirals?
Okay. Yeah. Good. I got an answer already. So any other answers? What kind of, maybe I'm on the way, what kind of curve this represents? If there was no t here, what would be your curve? If we just had sine t, cosine of t, and 0, what would be that curve? That's what also is, yeah, exactly. So, okay, oh, I have a lot of answers from class. That's good. Oh, there's, yeah, last question, the answer is circle, and then spiral up the z-axis, a spiral, a cylinder. Okay, so about the cylinder, we have to be careful. I know what you mean. It's not exactly a cylinder, but it's something that wraps around the cylinder, basically. So it's a curve, so it's a one-dimensional object. It wraps around the cylinder that you have in mind. So it's a spiral. I guess the reasonable word is a spiral. So this is something like this. So it moves up. So this is, for example, x-axis. This is y-axis, and as it was mentioned, this is the z-axis. But also it goes down, you know. So the z-axis goes to minus infinity to infinity and drops around. So the important thing is this part. If you project it down on xy plane, you always get its trace is just a circle. So the shadow of this particle that moves along this curve, if you study its trace or shadow as projected from up, right? It's going to be a circle on the plane, right? So on the xy plane, it's just a circle. But because there is this t factor, this t pushes this up or pushes it down. So it's not something in the plane, it's something in space, obviously. So that's okay. So one of the things that you should know in this section, this chapter, is that you should be able to have profiles of some of these things and identify profiles. The equation is given. I want you to draw a kind of rough picture that gives you the kind of idea of the shape of this curve. Not very precisely, but just a reasonable idea. Yeah, things like that. So here's another example. R of t equal to sine of 2t cosine of 2t and 2t. What kind of shape is this? What kind of curve? So what curve? So answer? Yeah, right. Cylinder, no. I got same, but stretched, no. Any other answers here? Yes. It's exactly the same curve, although it's going faster. It's just the speed of tracing is different because instead of t, we have 2t here. So each point is reached twice faster, that's all. Otherwise, it's the same curve, right? So the answer is geometrically it's the same curve. Rings are not further apart. Rings are completely same distance. Okay, there's a question, what's the difference between cylinder and spiral? Oh, it's a big difference. You see, cylinder is a surface. Cylinder is a surface, while a spiral is a curve. Spiral is one-dimensional. Cylinder is two-dimensional. They are very, very different. It just happens that this curve is wrapped around the cylinder like that. But that doesn't matter. I mean, the curve could be something else. It doesn't matter. It's just, they are very, very different. One is two-dimensional, the other is one-dimensional. It just happens that it lives on this cylinder, kind of, likes the cylinder to be on the cylinder. It's like, so that's what it is, and that's it. Okay, so there's an important idea here. We just changed the parameter here, but we didn't change the geometric nature of the curve. The curve is really the same. It traverses the same thing twice faster, but the curve is really the same. So this is called a re-parameterization, and that's a very important idea that we see coming along again and again and again. So that's very important in this section to pay attention. Okay, so that's one thing we have to pay attention. So now let me move on with the idea of continuity and, actually limit and continuity. So this is limit and continuity. So the question is, given a curve, function f of t equal to f1t, 2t, 3t. The question is, okay, so there's some discussions. So the question is, we want to understand what is limit of f of t as t goes to t0. What is this constant? So the limit of this curve is really a vector. So a vector say, it doesn't matter what I write, say I can just write A equal to A1, A2, A3 is the limit of f of t goes to t0. So we just say limit is equal to A as t goes to t0 if f of t gets close to A as much as we want if t gets close to t0 in a suitable way. If norm of f of t minus A can be made as small as we wish, by getting t as close as t0, by making absolute value of t minus t0 small enough. I don't write the exact epsilon delta definition. There is an epsilon delta definition that it doesn't matter. Just that the intuitive idea is enough by making absolute value of t minus small. Then it can be shown, so let me write it like this. It can be shown that this limit actually exists t goes to t0 is equal to A if and only if each of those components have a limit and they converge to the corresponding components over it, right? So if and only if limit of f1 of t as t goes to t0 is equal to a1, limit of f2 of t as t goes to t0 is a2, and limit of f3 of t as t goes to t0 is equal to a3. So everything can be reduced to this one-dimensional case, in other words, by this result. I won't prove this. The proof is not difficult, but it's not crucial to understand things in this course to know exactly the proof. It just writing amounts to writing this norm in terms of absolute value of these differences. That's not the big thing. Okay, so, and then because we understand the limit, now I can define the continuity, right? So we just say that this function is continuous. I mean, this vector value function is continuous if there is, if the limits exist, okay. So let me make a definition then. Okay, so I can erase this part. F from A, B to R3 is said to be continuous at t equal to t0 if and only if, first of all, limit exists and also not only the limit exists, but in fact the limit should be equal to the value of the function at that, right? So there are these two conditions. So exactly like the one variable case, it's formulated like that. And second, limit of f of t goes to t0 is equal to f of t0. So it's like two conditions should be should hold. In that case, we just say that the thing. Okay, now there is a result similar to what I did for continuity, namely the limit exists if and only if the limits of each components exist. That was what I said, what I did before. Now I just say that the function is continuous if and only if each of components are continuous. The same thing. So similarly, you may not remember now similar to what, because it was in previous page. So fact is this, that f equal to f1, f2, f3 is continuous at equal to t0 if and only if. So are you familiar with this notation, I double f? If and only if each of these factors are continuous at t0. If and only if f1, f2, f3 are continuous at t equal to t0. So we can reduce a lot of these questions to questions about limit and continuity of normal, usual functions from R to R, one variable functions. That's the domain of calculus, one variable calculus, right? So that's good. The more interesting topic now is to, I would say relatively more interesting topic is to study derivatives of such functions, okay? Derivative. Okay, so the definition of the derivative is exactly similar to this. We just say, so f prime, so definition is this. F prime at some point t0 is equal to limit of f of t plus t0, f of t0 plus delta t, I meant. T0 plus delta t minus f of t0 divided by delta t as delta t goes to 0, right? So that's the definition of derivative. And if the limit exists, if the limit exists, in that case, we just say that the function has a derivative at point t equal to t0, right? We say f is differentiable at t equal to t0. So now, at the surface of it, this definition looks like exactly like a one variable calculus definition. So the question is, what's the difference? Well, the geometry is different here, really. So we are really looking at this is a vector now, right? So this is a vector. We are dividing that vector by a scalar delta t. So the result is a vector. If the limit exists, it's going to be a vector. So let me draw a picture that will tell you what's the meaning of this vector. So basically, I want to tell you the geometric meaning of this derivative. So the best way to understand the geometry of this is to draw a curve in space like that. Okay, and then what we have? We have this f of t here, right? This is the vector f of t. I would say f of, say, t0, it doesn't matter. And then here, for example, here is f of t0 plus delta t. So this is this vector. Okay. And you're taking the difference between the two, right? You're taking f of t0 plus delta t minus. So this vector here, right? The vector here, this is f of 0 plus delta t minus f of t0, right? So let me put this under microscope and see what happens in this small piece. So it's like this, right? So we have this point, we have this vector, we have this point, and we have looked at this point. Okay, so this vector is f of t0 plus delta t minus f of t0. It's just this vector. And now what we are doing, we are letting delta t go to 0, right? So by letting delta t go to 0, it means that this point is approaching this point. Okay, you might guess, okay, then what? Then as we approach, in some good cases, like when the function is continuous, this length is going to go to 0, and this vector is going to approach 0. However, we are dividing by delta t. So that's a small quantity divided by a small quantity, and there's a better chance for that to have a limit. Because you divide small by small, you get something, maybe if you're lucky, you get into reasonable size. And that's the definition, right? So this is this vector, and we just look at these. So in the limit of f of t0 plus delta t minus f of t0 divided by delta t as delta t goes to 0 exists, then this is going to be a vector which is going to be like tangent to the line. Then that vector is tangent to the line, right? Then it represents a vector that's tangent to the line. And you understand why I call this tangent to the line, because this point is approaching this point. So you just look at it. I mean, this comes close, closer, closer. In the limit, it makes a kind of only one intersection with the line, and that means it's really closest possible straight line to the curve at that point, but that's not really intersecting the curve at other points, typically. That's the generic situation. So that's the idea. So what does this discussion tell us? The discussion tells us that there are several concepts that are completely related. One of them is the idea of derivative. The other one is the idea of tangent line or tangent vector to the curve. Can you tell me another idea which is completely relevant here, related to this? Derivative of space curves, tangent vectors, and can you tell me a concept from maybe physics? What concept in physics this reminds you of? And here by physics, I really mean basic physics. Velocity, yes, it's velocity. Exactly. Thank you. Yeah, indeed, it is the velocity of this particle that's moving on, along this path in space. If you want to measure velocity, that's exactly what you do. You just measure the distance. I mean, on the line, you measure the distance that travels, and then you divide by the time that it takes to travel that distance, that's velocity. We are doing a similar thing, but we are in space, so we have to be careful. We're going to get a vector. So that's the point. Okay, so in other words, I'm going to say that derivative, these three concepts are the same. Derivative equal to tangent vector equal to velocity. And again, it can be shown that if for f of t equal to f1t, f2t, f3t, the derivative exists, then the derivative of each of these guys exists individually. Then f1 prime is 0, f2 prime is 0, f3 prime is 0. Individually it should exist in the sense of calculus, because these are one variable functions, but in the sense of exists. And what is really nice is that the converse is also true. If those components are differentiable, then they are also exist. So, and conversely. So let me just, what a derivative reminds us of velocity. Okay, right. So anyhow, so that's the idea of tangent vector and velocity or derivative. They are all more or less. They are basically exactly the same. So let me give you now an example. Tangent line to a curve. So here's an example. So I ask you find the equation tangent line to the spiral. T equal to sine 2t, cosine 2t. Actually, I'm going to put here t, for example. It doesn't matter. At t equal to pi over 4. Now, you see, I didn't put 2t here. I just wrote sine 2t, cosine 2t, t. It doesn't matter. It's still, geometrically, it's like a spiral. It's just moving on the circle, except that the z velocity of it has changed now. So it goes with a different speed along the z-axis rather than the speed on x or y plane. Its trace on the x or y plane is moving with a different speed rather compared to the z-axis velocity speed. It doesn't matter. It's still geometrically is a is a spiral. It's not the same spiral though. Be careful. It's not the same spiral. It's a spiral. Right? Geometry is a spiral. So that's important to bear in mind. But so what we are trying to do in this question is something like this. So, so we have this spiral. And we want to, so there is this tangent line, right? So we want to find the equation of this tangent line. So to know the equation of the line, you know what you need. What do we need in order to get the equation of the tangent line? Okay, to get the equation of the tangent line, I need a point, which I do, which is this point is sine of 2 times pi over 4 cosine of 2 times pi over 4 and pi over 4. I would be careful about, yeah, I would be careful because I need the equation of a line. And you know, the equation of lines either comes in like symmetric form or vector form or this sort of thing. So you have to give me the equation of the line, but that's a good effort, yeah. Okay, so this is the point. So what is this point now? Sine of pi over 2 is 1. Cosine of pi over 2 is 0, and this is pi over 4. So that's good. All we need to know is the tangent is this direction, right? But the direction v is exactly f prime at pi over 4 is equal to f prime at pi over 4. What is f prime of v? So let's differentiate. You get twice cosine of 2t, right? 2 cos 2t. And then we have got minus 2 sine 2t. Am I still on? Yeah. And then there is a third component, which is going to be just 1. So from here, you get that, yes, f prime at pi over 4 is equal to twice cosine of pi over 2 negative 2 sine of pi over 2 and 1. All right? Okay, so this is equal to, well, this is 0, this is 0, this is minus 2, and this is 1. So this is the direction vector v. So what is the equation of the line now? The equation of the line is x minus x0 over a equal to b, y minus y0 over b, and so on. So let me write it down then. X equal to x0 plus at, y equal to y0 plus bt, z equal to z0 plus ct. This tells me that x is equal to, well, this is x. I erased my x0, y0, z0. So what is x0, y0, z0 I derive? X0, y0, z0. This was f of pi over 4. That was the point. So what did I derive? 1, 0. Thank you. So, okay, so I've got 1. And of course, this is equal to ABC, right? So A is 0. That's good. So that's equal to 1 plus 0. Y is equal to, now y0 is 0 plus b. B is minus 2. This is minus 2t. Z equal to z0. Z0 is pi over 4. And then plus ct. C is 1 plus t. Okay, so that's good. That's the equation of the line, of the tangent line. I don't write articles all the time. That helps me. Just bear with me. The articles. Equation of tangent line. Sometimes you want to write like newspaper headlines. They don't have enough space, so they have to shorten. Okay, so any questions about this? So let's see. From home, I don't have any comments. Good. Any questions here? Okay, so the equation of the tangent line, we can certainly write using everything that we learn about these things. Now, what else? So now there are some rules of calculating the derivative, because it could be difficult sometimes if you want to go back to basics, right? I mean, you want to have some rules that are kind of akin to vector operations and tells us how to kind of do the derivations with respect to these different vector operations. So that's very important. Okay, so let me erase this part. So I just write it as some useful rules. I mean, I just say rules of derivatives. So, I mean, one of the basic things is if you take the dot product of two vector fields, or I mean, two such vector functions, what is the derivative of this? The first one is like, what is d dt of f of t dot g of t? Well, this is going to be equal to I just write it like this: f prime of t dot g of t plus f of t dot g prime of t. What kind of rule this reminds you of from calculus? This is supposed to remind you of a rule in calculus for calculating derivatives. What rule was that? Product rule. Yes, that's a vector value version of the product rule. How would you define this? I mean, how do you prove this? Exactly. Let's prove this. I mean, just for fun. Let us write f of t equal to, I just write f1, so let f equal to f1, f2, f3, g be equal to g1, g2, g3. Then let's do just f dot g equal to f1 g1 plus f2 g2 plus f3 g3. Okay, and then fg prime. That's what we want to do. We want to calculate the derivative of dot product, right? So this is equal to f1 g1 plus f2 g2 plus f3 g3 prime. We want to take derivative of this. Now we are back to calculus. So we use what we know from calculus. So this is equal to f1 prime g, as you said, product rule, plus g1, sorry, plus f1 g1 prime plus f2 prime g2 plus f2 g2 prime plus f3 prime g3 plus f3 g3 prime. So what you do from this step now? It looks like we have got a very complicated term. We have like 6 terms now, but here we have 3 terms. Oh, sorry, we have 2 terms here. Here we have got 6 terms. What's the relation between this and that? Can you finish the proof, in other words? You could, yeah? because I can write this still in terms of dot products. I can write it as f1 prime, f2 prime, because this is, just keep that, f2 prime, f3 prime, dot, g1, g2, g3, plus, and the other one is f1, f2, f3, dot, g1 prime, g2 prime, g2 prime. Okay? Now that we are good, because this is equal to f prime as a vector dot g plus f dot g. So you see, everything can be reduced to the case of calculus, but we have to know what you're doing, of course. Otherwise, you can end up in a mess. So this is a very beautiful, very nice, useful rule. Extremely, actually, useful rule. Because you know, we avoid doing these intermediate calculations in every problem. We just use the answer. By the way, do you know another rule, another name for product rule by any chance? Huh? No, it's very different compared to chain. Any other name for product rule? It's name of a mathematician. That's why I care and I mention it. Which mathematicians? What mathematician's name? Yes, exactly. Thank you. Leibniz. Yes, this is also known as Lightness Rule. So when Leibniz was inventing calculus together with Newton and others, he didn't know about this rule. He just wrote EDT of f of t times g of t is equal to f prime of t times g prime of t. He thought he would take the root of that, and then he did some examples for himself, and he said that, oh my God, this is not correct. So he corrected it, and then then he was able to prove it. Okay, guys, thank you so much. So any questions? Because we're done now. Okay, so if there are no questions, maybe we should at least stop the video and then we can just talk a little more still. Pause record.